Okay, our first speaker of today, no less than Sebastian Haro from the University of Amsterdam. A conceptual analysis of black hole entropy in string theory.
Thank you. Can you hear me? Okay. So, yeah, I would like to thank thanking the organizers, especially Gerard and Damon, and also Gert, for the invitation to speak at the conference. It's a great honor to be here. I'm going to present some work that I've done together with Jeroen van Dongen, who will speak after, and also Manus Visser and Jeremy Butterfield, who also speak at the conference. And I will highlight some of, I will talk about the calculation of black hole entropy in string theory and highlight also how Gerard's contributions have also helped mold some of these ideas that went into that calculation, and especially the developments that came after. But after all, we're here to celebrate Gerard. So, well, 20 years ago, I was Gerard's PhD student here in the Minard building. And when the announcement came, it's one of those moments that, one of those moments that you remember exactly where you were when that announcement happened. So I remember I was in my office, and Maulik Parik, whom some of you may know, he was a postdoc at the time, and what I remember is that he came running down the hallway shouting, "It's Gerard, it's Gerard!" and then we all gathered and congratulated Gerard. But also, you know that Gerard has received many awards. He has an asteroid named after him. And actually, I would invite you to visit the asteroid if you have a chance to get on a shuttle, maybe this summer or maybe next year. But you should know that there's a constitution that has, I think it has not yet been approved, but it may be approved soon. And it's very easy, it's very simple. So it has a number of articles about the territorial zone of the asteroid. You should know that if you go there, you need a visa. All aliens embarking on the 9491 at Hoofd must be in the possession of a visitor visa. The big one is the one I would recommend. There's also an immigration visa, but then you might get trouble coming back. However, don't worry, because Article 3 says that the amount of bureaucratic hassle required for obtaining any of the visa above shall be at all times less than 1/2 of what foreign postdocs and their families must endure when they wish to take a temporary appointment in the Netherlands. This emphatically includes the town of Utrecht. All bureaucratic regulations issued to apply to the inhabitants of visitors of 9491 at Hoofd will be only effectuated when and where they serve a reasonable purpose. So it will be an easy process, don't worry. There are some other regulations, I'm not going to read them all, but some of them are very important concerning conventions. So there are conventions that you have to stick to. For example, all industry on 9491 at Hoofd shall make use of either metric units or Planck units, with exception of the time units described in Article 12. In particular, miles, inches, and gallons are outlawed. The use of ESU, INU, or Gaussian is forbidden. The metric tensor, and that's very important, it's signature minus plus plus plus. So that's a piece of information that you should know if you go. If you want to learn to pronounce Gerard's name, there's a website where you can listen to it. It's a big hit. That's 14 visits already. So it's Gerard. So before you get there, you might want to listen to it. Okay, let's get back to black holes now. So in this talk, I want to present the microscopic state counting of the extremal black hole performed by Strominger and Cumrun Vafa in 1996. In its contemporary context, so I will look at it from a historical, philosophical angle. So I would like to analyze or present the argument's conceptual structure, which is actually rather intricate, and to identify the various inter-theoretic relations that go into the argument. And so what we would like to understand in this project is why the argument was immediately recognized by the string theory community as a successful account of the entropy of this particular black hole, and also the subsequent work that it engendered, in particular in relation to the ADS-CFT correspondence, although it will be very brief there. And then there are two further philosophical questions that I will also briefly highlight. One is the question whether the black hole is the same physical system as the system of D-branes where the calculation is done. And the second question is whether we can say that the black hole is emergent from the D-brane system. And I will explain these terms in a minute. So here's an outline of the talk. It has three parts. First, I will review some string theory to get the concepts. Then in the second part, I will present the calculation. And then the third part, I will say something about duality and emergence for this particular black hole. Okay, so recent discoveries, also astronomical discoveries, and through the use of gravitational waves and the Event Horizon Telescope, suggest that black holes do exist in nature. There is good evidence for that. However, there's still many things that we don't understand about black holes. For example, space-time singularities, the information paradox, black hole entropy. Theoretically, a key proposal for the entropy of black holes was made by Jacob Bekenstein. It had already been the laws of black hole dynamics had already been postulated by Bardeen, Carter, and Hawking, so an analogy with thermodynamics had been postulated. And then Jacob Bekenstein calculated, give a counting argument for the temperature, for the entropy of the black hole, but the calculation was done with all the correct coefficients, famously by Stephen Hawking, who also understood that black holes radiate and that they have a temperature. Recently, philosophers have been interested in these topics. The famous Bekenstein-Hawking formula for the black hole is here. So it relates the entropy of the black hole to the area, and then here's the coefficient that Hawking calculated. Now, in supergravity and string theory, black holes were known since the 1980s, black hole solutions of supergravity by Gibbons, Haro, and others. However, in 1996, Strominger and Vafa posted a short article in the HepTH where they did the first microscopic calculation of the entropy of a black hole in string theory. And so in the eyes of many string theorists, this provided the first convincing account of the entropy of a black hole from a microscopic perspective, and it was taken to confirm the Bekenstein-Hawking formula. Now, this calculation in 1996 followed closely a number of developments that there had been in 1995 and earlier, especially Edward Witten's duality conjectures, where he postulated that various string theories were related to each other, and to another theory that he conjectured, which is called M-theory, and Polchinski's discoveries of D-branes, and we will have, I believe, more talks about dualities during the conference. So this microscopic counting was perceived by string theorists as one of the major successes of their theory, and this particular paper has been very highly cited. Now, Strominger and Vafa's calculation also played a pivotal role in the developments that followed in the following years, especially leading up to ADS-CFT conjecture. And actually, the ADS-CFT conjecture is one of the places where two of Gerard's ideas have played an important role, namely the large n limit of Gates theories, which Dean Rickles will talk about later in the conference, and also holography, which has already been mentioned during the opening comments. Now, the Strominger-Vafa result is more than 20 years old, so we felt that the time was ripe for philosophers to look into this result. and the various generalizations that have been done of it. However, one first problem one encounters that the paper is only 11 pages long. It's very short. It was written during a frantic period of activity in the 90s, where basically most string theorists had been reading about dualities in the year before, so they all knew what these dualities were about. So the paper itself doesn't really do a lot of explanation for outsiders. So that's the reason that I will review some of this material. So our project aims to give a historical philosophical analysis of the argument and to outline its contemporary role in string theory debates. Now, to summarize the argument, and later on we'll discuss it in more detail. It has 4 components, so 4 theories that are being related. On the one hand, supergravity, which is Einstein's theory of relativity with additional fields that make it supersymmetric, so there's a symmetry between bosons and fermions. This theory contains black holes, so we will look at black hole solutions in supergravity. Then a theory of strings that interact with higher dimensional objects that are called D-branes, and I will say more about that in a moment. The third theory is a theory describing the dynamics of the D-branes themselves. So this is the theory on what we call the world volume of the D-branes, so on the D-branes. And the fourth theory is this conjectured end theory that underlies these string theory dualities. Now for my talk, this last theory will not play a big role because also in the Strominger paper, M theory was maybe a guiding principle. It was part of the goal to discover something about M theory, but it didn't enter the actual calculations. So the argument uses a conjectured duality between supergravity and these strings, these open strings, and there are also linkage relations between the others. So the Strominger paper presents a calculation of the number of microstates for the D-branes in this system, and then this calculation is extrapolated and compared using duality to the Bekenstein-Hawking formula that is calculated over here in supergravity. So it's a relation between this theory and supergravity using the open strings. So there are 2 main assumptions in this argument. One is duality, I've already mentioned it. Duality between open and closed strings suggests an identification, some sort of identification between theories 1 and 3, so the black hole and the D-branes, via the open strings. What kind of identification? Well, it's some kind of equivalence between theoretical structures, or we could say the same formal theories for different ranges of the relevant quantities. I will discuss that it seems that it is not quite a duality, but it's close to a duality, so far as we know. The argument does not actually require that these 2 systems are the same. It only requires the formal agreement between the systems. And the second important ingredient that goes into this extrapolation is supersymmetry. Supersymmetry of the various systems justifies the comparisons of their entropy at different values of the relevant quantities, in particular the coupling. Because the entropy is guaranteed to be invariant under suitable changes of the distance scales and the coupling due to supersymmetry. So this is why the argument is for what is called an extremal black hole. We'll say more about that in a minute. Now, one of the first generalizations that were done in the same year is that the argument was applied to non-extremal, so near-extremal black holes by Cullen and Maldacena. So let me review some of the basic concepts in string theory that went into this calculation. So we have basically 3 important types of objects in string theory. Open strings, you see here a picture, so the open strings are like little pieces of rubber, so one-dimensional objects that can vibrate quantum mechanically. They carry non-abelian charges at their endpoints, and their endpoints in the theories that we are considering are attached to these hyperplanes called D-branes. So D-branes, for our purposes, can be seen as hyperplanes on which open strings can end. They source the non-abelian charges of the open strings. And furthermore, there are these closed strings, which can arise, for example, when an open string detaches itself from the D-brane and the endpoints are joined. These closed strings, they are the carriers of the gravitational force. So you see that the contrast between open versus closed strings is very much like the contrast between nuclear type forces, non-abelian Yang-Mills type forces, and gravitational forces. And furthermore, there are two fundamental constants in this theory. One is the string length, Ls. I will often write it in terms of alpha prime, as is usual in the field. So alpha prime is the string length squared. So it's the fundamental length of a string. And in the point particle limit, when alpha prime goes to 0, the string looks like a point particle. The second constant is the string coupling, which measures the strength of the interaction between strings, very much like for particles, the interactions are measured by a coupling constant. Also here, there's a coupling constant that determines the strength. Here we have interactions between closed strings. So at each vertex in this Feynman type of diagram, each vertex comes with a factor of the string coupling. Okay, so we will consider what are called type 2A and type 2B string theories. These details will not actually be important, but I will occasionally mention that jargon. For us, the distinction between these theories is in the dimensionality of the D-branes that they can have. But again, that's just a piece of jargon that won't play an important role here. The second piece of jargon that I will use is I will talk about open string theory, when I will actually mean the open string sector of the full string theory. And this is the usual physics jargon, so we concentrate just on the open string sector of the full string theory. So string theory contains both open and closed strings in general, but sometimes you are just interested in the open strings or just interested in the closed strings. Okay, so I have now said something about strings and the objects that come with them, and the D-branes. Now there's a further theory that we need, which is supergravity theory, which is a version of general relativity, with additional fermionic fields that make the theory supersymmetric. So at low energy string theory, in particular closed superstring theories, are well approximated by semi-classical supergravity theories. By low energies or large distances here, I mean that the string length goes to 0 compared to the typical size of your system, or more precisely the typical distance at which you probe the system. So the length scale at which the system is probed. Okay, so as is well known, string theories require 10 space-time dimensions for their mathematical consistency. And so do the supergravity theories that we will consider, which come from these string theories, also live in 10 dimensions, but they are compactified down to lower dimensions. So they are placed on small spaces, so one assumes that the space is small, such that the world looks effectively 4-dimensional, or in one of the cases 5-dimensional. Okay, so I have now introduced the various theories, and I now have to say something about two key developments that led up to the Strominger-Vafa calculation and what is called the second string revolution, both of them in 1995. So Edward Witten gave evidence for a series of dualities connecting string theories with each other and with 11-dimensional supergravity. And really, there were a lot of people involved in this project. It wasn't just Edward Witten's paper. There were so people like Michael Duff, Carlo Stella, and many other people contributed. So this was a huge program in the early 90s how to connect string theories and supergravity theories. Key ingredient of that was a so far known class of states of the closed string theory, supersymmetric quantum states whose semi-classical limit are black holes of supergravity. So this, so Witten discovered that basically in string theory there were some states that hadn't been seen before, and these states he conjectured that they were related to black holes. The distinctive feature was that their mass is proportional to their electric charge, and they were inversely proportional to the string coupling. So these black holes were already known. They were known as P-branes solutions. So P-branes are solutions of supergravity theory. The P stands for the dimensional, the spatial dimension of the brane. So these are solutions of supergravity. They are like hyperplanes in supergravity that have horizons. And when you compactify them to, say, 4 dimensions, they look like points. And so they look like black holes with horizons. So these solutions were already known, but it wasn't known that they are states of closed string theory. And they have 2 important properties. One is that they have the minimum mass possible for a given charge in supergravity, given by this bound over here. So they cannot lose energy. They are stable solutions. They do not Hawking radiate. And they also have 0 temperature. Yet their entropy is non-zero. Their quantum equivalents were identified as degenerate ground states of string theory. The second important property is that they become infinitely massive at weak coupling because of the inverse dependence on the coupling. So when the coupling is weak, they are infinitely massive, so they cannot be made of ordinary weakly coupled strings. They are rather something like solitonic states. Now, so some of the jargon that is used in the literature is to say that they are non-perturbative states or BPS states for Logomoni, Prasad, and Sommerfield. Now, the second development in '95 was that Polchinski introduced again his D-branes. He had discovered them together with others in 1989. These D-branes were, like I said at the beginning, they were defined as the endpoints of open strings. And now using the conjectured open-closed duality, he identified D-branes with its BPS states in string theory. So what Witten had conjectured were states of string theory that correspond to supergravity black holes. Polchinski now identified with his D-branes. So he wrote, Polchinski wrote in his memoirs, at the end of Witten's talk, this is in 1995, my green and I looked at each other and said, that looks like D-branes. It was a shockwave for me and the rest of the field. I had been living with D-branes for 8 years, but never taking it too seriously. But for almost everyone else, it was a new thing. String theory had D-branes as well. His paper, he had a number of points of evidence for this identification between D-branes and Witten's BPS states. He calculated the mass of the D-branes, and that agreed with Witten's result, the number of supersymmetries. Also, he showed the D-branes coupled to the appropriate gauge fields on the world volume and a number of other things that I will not go into in detail. Now, what is the relation between these D-branes that Polchinski found and the P-branes that were already known in supergravity since the 80s? So remember, P-branes are the supergravity black hole solutions that were already known, and Witten incorporated this into string theory. They are solutions of closed string theory, while the D-branes are the endpoints of open strings. The D here stands for Dirichlet, so that has to do with the kind of boundary condition that the open strings satisfy. So they are different, but now, according to Polchinski, there's a duality relation between them. He also wrote in his memoirs, as Andy Strominger had reminded me, he, Gary Horowitz, and I had lunch together nearly every day for 3 years without realizing that their D-branes, introduced by Horowitz and Strominger in 1991, and my D-branes were the same. So they were very a priori different looking objects, but now they found that they are actually the same. So Polchinski's discovery was an extension of the open-closed string duality, which had been known in perturbative string theory since the 80s. So when people were calculating Feynman diagrams in perturbative string theory, what they found is that an amplitude like this one, and well, this is Polchinski's calculation, so this one includes D-branes already, but in the early string theory, these calculations have been done without D-branes. So here you see two open strings interacting, so they create, they go forward in time, and then they annihilate. This type of diagram had been identified with this type of diagram, where now this cylinder on which these open strings move is reinterpreted as an interaction between the D-branes, so the emission and absorption of a closed string. And so Polchinski's kind of heuristic explanation of this is that a different choice of time slicing gives you the identity between these two. I hope this time slicing respects Gerard's convention about the metric test, otherwise you will get the wrong result. Now, this approximate duality to D-branes can be applied to these D-branes with BPS black holes, and that underlies actually the Strominger Vafa result. So on the one hand, we have the open string D-brane system. On the other hand, we have the BPS black hole stays in the supergravity limit of the closed string. So here you have a picture between the two objects that this conjectured open-closed string duality is supposed to relate. Okay, let's go in a bit more detail into this open string side of the correspondence. So let's focus on the dynamics close to the D-branes rather than on the long-distance phenomena. So we probe, in physicist jargon, we probe the system at short distances such that the probe distance r compared to the string length is much smaller than 1. And we probe it using another D-brane. So we have a stack of D-branes sitting relatively close together, and we have now another D-brane at this distance r, and we are now going to probe these D-branes over here by putting this D-brane close to each other, and then seeing whether there's a force between them. What is calculating the force between them? That's something that Alessina did. So Witten showed that this dynamics is given by a Yang-Mills type of quantum field theory living on the world volume of these D-branes. So the theory that describes the interactions between the D-branes, as you see from the response of these D-branes to the presence of those D-branes, is given by a Yang-Mills type of theory, a non-abelian gauge theory. It is a conformal field theory, a locally scale invariant quantum field theory. So here we go from a situation of long distances to short distances already, probe distances. Now, in a paper by Douglas, Kavat-Pulil, and Schenker illustrated this duality in more detail. They did it for various D-branes. They showed that it gives a relation between the world volume theory of the D-branes and supergravity. So they exhibited more explicitly how supergravity reproduces the kind of Yang-Mills amplitudes that you get from the D-branes. So what they found is that for small probe distances, the interaction between the D-branes are described by the infrared behavior of the world volume theory. So the infrared regime of the world volume theory describes short distances in string theory. This is surprising because in quantum field theory, normally the infrared regime is associated with long distances, low energies. Here, it is associated with short distances. this is the infrared ultraviolet connection. And it is ascribed to the extended nature of strings between the D-branes. Now this calculation, an important, again there's an important ingredient related to Gerard's work on the large n limit. So actually, in the presence of D-branes, the relevant string coupling is not GS, but rather GS times the number of D-branes. So that's called the Evaporation coupling. And in what follows, the number of D-branes will be basically the D-brane charge, because each D-brane is taken to have an elementary unit of charge. Okay, so that's the background that led to the Strominger-Vafa calculation. So now I can show you the Strominger-Vafa calculation, and actually I've done all the work already. So to carry out the calculation, Strominger-Vafa needed to establish a connection between these three systems that I have talked about. On the one hand, the black hole. On the other hand, the open string system. This relation was Witten's duality conjecture as realized by Polchinski. And now, to do calculations, to do entropy calculations, we had to go to this infrared limit of the theory, to these long distances where we can use this Daniel's theory to do calculations about the open strings. And as you see here is M theory sitting there, but I'm not going to say much about it today. Along this direction, in this direction I have the radial distance, in this direction I have the Evaporation coupling. So when we go from here to here, we have to extrapolate the Evaporation coupling. So here we are doing a perturbative calculation with coupling calculation, the Evaporation coupling. Here, the Evaporation coupling is large. Okay, so I'm going to look in more detail at this system and at that system, but especially the black hole system. So the Strominger-Vafa black hole is a 5-dimensional Reissner-Nordström black hole. It's an extremal black hole. It's a solution of, so extremal means that it satisfies the BPS bound that I showed before. So its mass is given by the charge, so it has the minimum mass. Possible is given by the charge divided by the string coupling. Here's the metric for the black hole. So RH is the horizon, R is the radial distance, and it's a 5-dimensional black hole. Why 5-dimensional? Well, just because it was the only system for which they could do this. So it was hard to do this calculation for 4-dimensional black holes, although very quickly the calculation was also done for 4-dimensional black holes as well. Here you have the expressions for the radius of the horizon expressed in terms of the charges. This black hole has two charges, two different charges, QF and QH. There are two different types of electric charge, two different gauge fields. And then the Wittgenstein-Hawking entropy, which is calculated from the area of the black hole. Now, the validity, this calculation is a supergravity calculation, it's a semi-classical calculation. It's valid if the horizon is much larger than the string length, because otherwise we would have to take really if the horizon were too small, we would really have to take the quantum string effects into account. And also, the string coupling also has to be small. And in terms of the charges, this is the condition that implies. So this is just a reformulation of these two conditions in terms of the charges. So this is to say basically that we have to be at low energies and low couplings, low string couplings. Now, what are we relating? So we're going to relate the Wittgenstein entropy to the entropy of the D-branes. So the D-brane calculation is valid if also the string coupling is small, but the Evaporation coupling is weak, which means that it gives this condition and that condition, and that's a different condition from the ones we had before. So there will be an extrapolation here. And here, in the interest of time, I'm not going to go through details, but basically here are the details about the type of configuration that they took. So they took a number of D-branes, D1, D3, and D5 branes, so 1-dimensional, 3-dimensional, 5-dimensional D-branes. They wrap them on some cycles of this internal manifold. Remember, we go from 10 dimensions to 5 dimensions by compactifying on a 5-dimensional manifold. They wrap these D-branes on this internal manifold so that the system looks like a point particle in 5 dimensions. So it looks, from this supergravity perspective, it looks like a black hole. But I'm not going to go into those details. So then, so the key fact here was to identify the configuration of D-branes that would correspond uniquely to this black hole. And so to do that, two steps remains. First, we need to specify the theory on the world volume theory of these D-branes. The relevant world volume theory turns out to be, it's the intersection of the D-branes. It turns out to be an H1 times R. R is time. So there's it's a 1 plus 1 dimensional conformal field theory. So these D-branes intersect along a circle, and there's also time, basically. So there is a 2-dimensional, 1 plus 1 dimensional conformal field theory on the D-branes. That was the first step. The second step was to calculate the degeneracy of states in this theory. And to do that, they used Carter's formula. So they, in conformal field theories, 2-dimensional conformal field theories, there is a formula that counts the number of states at given energy. It's given by this formula asymptotically for large energies. Now here, the energy is given in terms of the charges in this way, so the energy is proportional to charge, and C is the so-called central charge of the conformal field theory. It characterizes what kind of conformal field theory you have, namely, it counts the number of fields, roughly, that you have in the conformal field theory. So using this degeneracy of states, this is a quantum mechanical calculation that can be done in a 1 plus 1 conformal field theory. That gives you the statistical entropy for this given energy, so the degeneracy of the states with that energy, given by the logarithm of the density, and it is given by this formula over here. Now, to compare the two calculations, remember that we are in different regimes, and so we have to extrapolate from one regime to the other, from weak coupling to strong coupling. In the supergravity, the charge is very large. So basically, in the supergravity approximation, this UF squared is much larger than the factor of 1. So if we drop the factor of 1, you see that the formula agrees with the Bekenstein, with the area, with the Bekenstein-Hawking entropy of the supergravity black hole. So Strominger and Vafa assume that the Carter formula is still valid for very large charges, in which case the formula precisely matches the Bekenstein-Hawking formula. So this is the main Strominger-Vafa result relating the Boltzmannian entropy for the D-branes to the Bekenstein-Hawking entropy of the black hole. And that match is guaranteed by supersymmetry. It's actually a topological argument that they use to extrapolate from weak at-Hooft coupling to strong at-Hooft coupling. Okay, so that's the main result. How do we analyze this result? I've already discussed this. So we have done a calculation over here, a calculation over there. We have used the relation between this system, and that duality, extrapolating the couplings to match the two results. Okay, I'm going to skip the slides about M theory.
10 minutes.
10 minutes.
You have 15 minutes including discussion.
Okay. So there are two idealizations which I've already mentioned, on which this argument crucially depends. One is supersymmetry. So the black hole is extremal, which means that its mass is the minimum mass is given by the charge of the black hole, and so supersymmetry ensures that this calculation can be extrapolated. But it would be desirable to do this kind of calculation also for non-supersymmetric black holes, of course. So to go away from the pure extremal limit. So to do this for other black holes. Now, even if we would not succeed in doing such a calculation for, say, a black hole of zero charge, like the astronomical black holes that we see in the universe, which have typically zero charge, or very small charge, even if we wouldn't succeed to doing calculations for those type of black holes, already doing calculations for black holes with different, which are non-extremal, with different masses, that would already be quite interesting. The second is that this was done for 5 dimensions. So of course, if this was only valid for 5 dimensions, what one might argue, well, it just happens to, it's a coincidence, it just happened to coincide, but how do we know that this also holds for 4-dimensional black holes? So the question is, did subsequent work go beyond these assumptions? And indeed it did. So Kalman-Malesena took in 1996 5-dimensional black hole with a mass that exceeded the extremal value by a small amount. Of course, always in physics, when we want to go beyond an idealization, what we do is always first the harmonic oscillator, the first correction to the ideal result. So this is the, so now this black hole had 2 horizons, and the mass can be expressed as the mass of the extremal case plus a small correction. So it's the charge plus a small correction. Now, this black hole explicitly breaks the supersymmetry, but in spite of that, the microscopic and macroscopic calculations still agree. So they calculated the correction to the entropy divided by the extremal entropy, and that is given by the square root of the correction to the mass divided by the extremal mass. And now this black hole has non-zero temperature. It's no longer a ground state. It's emitting Hawking radiation, and the value is given by this. So they calculated the radiation rate using the D-branes, and this confirms the black body spectrum predicted by Hawking. The mechanism for the evaporation that they suggested is that the open strings on the D-branes collide to form closed strings. So they detach themselves from the D-brane, they come off the D-brane, and they are emitted as closed strings. Of course, one has to remember that in doing that, there is a weak coupling, strong coupling, evaporation. So that particular explanation of the Hawking radiation is a heuristic explanation that you have access to at weak coupling. This calculation was also done for 4-dimensional black holes by Malesena, Strominger, Johnson, Curry, and Myers, and I'm going to go into that. Also for rotating black holes, this has been done, and also for other types of black holes. This was also done in ADS CFT. Better said, the Strominger Vafa calculation was a crucial step in the development of gauge gravity dualities, and maybe on Saturday we will hear more about this from Malesena. So the calculation itself can be reproduced and generalized in ADS CFT, including for non-extremal situations, such as, for example, the BTZ black holes. And so since then, there have been very many generalizations of this type of calculation, and I would say that the understanding the physicists now have of this type of calculations much better than it was in 1996. It's a huge field with lots of questions also for philosophers and historians. Okay, and now I come to the last part of the talk, more philosophical. Duality and emergence for the Strominger Vafa black hole. So this calculation calls various questions. One is whether this black hole, we are comparing quantities of 2 systems, we're comparing entropy. So one question is whether the black hole is the very same physical system as the system of D-branes. Are we talking about the same system, or are we just comparing formal properties of 2 systems that happen to have the same entropy? So we have broken up this question into several sub-questions. One question is, must any 2 systems related by duality be the same? So remember that the duality underpins this calculation, the comparison between the quantities. So is duality enough to guarantee that those systems are the same? Our answer is no, not always, because duality is a formal relation, so we could, after all, have formal relation for, we could have an isomorphism of systems that are physically distinct. That seems possible. The second question is, did string theorists believe, or do they now believe, that the two systems in the Strominger-Vafa argument are in some sense the same? We will answer broadly yes. Of course, to make this consistent with our first answer, one has to say, well, maybe there must be some other argument why these systems are maybe not exactly the same, but roughly the same, why they correspond one to another. And the third question, is there a rigorous duality between open and closed strings in the Strominger-Vafa scenario? So our answer will be apparently not, because the current evidence is not conclusive to the existence of a duality. In this case, in ADS-50, the duality seems to be much more robust, but in this case, it isn't. So that comes the question, maybe we should think about the black hole as not as identical to the D-brane system in the philosophical sense, or in the strict sense, but rather as emergent. Okay, so question of same systems. So a duality is an isomorphism between two physical theories, and the isomorphism preserves the states and the quantities and the dynamics of the two systems. But since isomorphism is a formal notion, two dual theories can have different subject matters. One has an isomorphism between the easing model at high temperature and at low temperature, and clearly high temperature and low temperature are two distinct situations, so there is no a priori reason why a duality should relate identical systems always. So this bears on the Strominger-Vafa argument. If the two systems can be thought of as being the same, then there is little reason to doubt that the argument is correct. So if the two systems, if we had an argument to the effect that the two systems are the same, then we would be fine. Then the argument would really explain something about the microscopics of entropy. But it is not at all obvious that they are the same. And so if not, then one may wonder whether the black hole entropy has been explained by the D-brane quantum. So this brings us to the second question. The string theorists believe that the two systems are in some sense the same, but at different couplings. And our conclusion is that yes, for example, Haro and Maldassena and others in an important review write that the extremal P-brane in supergravity and the D-brane are two different descriptions of the same object. So they use this word, the same object. Is this equivalence justified? So let's look at question C now, what duality could... I should, in all fairness, I should say that Haro et al. They distinguish various levels in which these two theories can be equivalent. So this is the strongest version that they consider. They also consider weakenings of this statement. So to the best of our knowledge, the present consensus is that there is not a rigorous duality between open and closed strings in the case of the particular Strominger-Vafa scenario that they consider. So there is only an isomorphism of the perturbative expansion of the open and closed theories, which is sufficient to ensure that the entropy has the same value. It's protected by supersymmetry, but it is not sufficient to ensure that the two theories describe the very same system. So a full isomorphism is only expected, in the words of Johnson, when there is a complete decoupling of the supergravity description from the gauge theory. That's precisely what happens in ADS-CFT. You focus on the near horizon region, only on the open strings, and in that case you get a decoupling between open and closed strings, and then you have a full isomorphism. So that actually led UvA to considering, Maldassena to considering ADS-CFT. Yeah, I'll finish. So this leads us, so this weakening of the identity doesn't need to undermine the validity of the identification of entropies, because first of all, the same function has been found for different types of black holes, so the duality does ensure for us that the quantities should agree. Furthermore, the BPS nature of the D-brane ground state that's what I just said. Yet we would like to have a more direct relation between the two quantities. So that's why one might want to think of it in terms of emergence. And I will just mention this, and then maybe Jeroen will say more about that in his talk. So there are various suggestions in the literature that this might indeed be a case of emergence. For example, Johnson says that the P-brane is made of D-branes, so you could think of these P-branes as kind of the macroscopic objects consisting out of microscopic kind of building blocks of constituents, and we could think of these of this macro state that is the black hole as emerging from the micro system. Okay, so the emergence relation would be from the D-brane system, which is the macroscopic theory where we can do quantum mechanical calculations, to the macroscopic black hole. Okay, I will have some slides on what is emergent, but I'm going to skip that. Now, if one claims that the black hole exists, then it should be the case that not just the entropy, but also the metric itself emerges in the right signature, in the right type of signature. So it turns out that one can calculate the metric of the near horizon region of the black hole from the D-brane system. So this is a calculation that was done by Douglas and others in 1997. They calculated the effective action for the motion of a D1 brane in a background of D5 branes. So basically the metric of the black hole comes from what is called the moduli space metric, so the metric in the space of fields for the D-brane system. And when you do an expansion in large R, you find precisely the right metric. However, there was a disagreement at two loops, but Juan Malacena, in a lecture in Strings 97 in Amsterdam, he said that he reported that it was probably all fine. The D-brane action had the right structure, and that of course led him to ADS CFT because he was focusing on the near horizon area of the black hole. Okay, now eventually one would like to get the entire black hole metric, not just the perturbative expansion of it, and that at least for the region outside the black hole, and I'm sure Malacena will tell us more about that, can be done much better in ADS CFT, and also here we developed some techniques for doing that, for extracting the bulk metric from the boundary data. Okay, so I'll summarize. Our conceptual analysis shows how the Strominger-Vafa calculation was rooted in well-established principles of duality. These they were regarded as sound by string theories at the time. That explains, that makes clear the internal consistency of the argument and how it agrees with the overall picture of dualities in string theory. Some of the generalizations of this result, especially the calculations for non-extremal black holes, spinning black holes, four-dimensional black holes, made the result more physically significant, and so that gave it a wider appeal in the community of black hole physicists. And also it spawned a wave of work from the late 90s, which continues up to today. It laid the foundation for many developments in the field. It also raises a wealth of interpretive issues. I think we have just scratched the surface with these two questions about duality and emergence. So our analysis suggests that the D-brane states that are counted can be seen as the quantum states of a black hole, but not in the strict sense of identity of systems, but rather in this weaker sense of that there is emergence. So we are comparing a macroscopic object with a quantum mechanical microscopic object. However, this depends, of course, on various issues which are still unsettled in the physics literature, like, for example, the status of open-closed string duality. So it seems current knowledge seems to indicate that it's not an exact duality, but this might change in the future. So that particular aspect is still undecided. So thank you very much.
Thank you. I think we have time for, well, a few questions only. But so there's time for one or two questions.
Testing.
Sure. And then David will throw around the microphone. Did I say throw around? Yes, I said throw around because it's actually a microphone you can. Oh, yeah, give us a. Just speak in. Do you have a question?
This is sort of. Hello, can you hear me?
Yes. A bit closer.
This is a sort of comment on your question about whether the D-brane states are necessarily sort of what is a black hole or what accounts for the black hole entropy. What they started considering was these extremal black holes. They have a charge. If there are no other objects in the theory besides the D-branes that carry that charge, well then you need the D-branes to make those black holes. But of course there are also D-brane solutions that are uncharged in the theory, which, and just like in general relativity, where we could make a black hole with gravitational waves without even any matter, the same thing could presumably happen in string theory.
Would those black holes be supersymmetric?
Or,
Would they be supersymmetric?
no.
Okay, so there would be different configurations.
A black hole that was formed from gravitational waves or something, just closed strings, no D-branes are implicated, and yet this black hole has an entropy. So certainly, I mean, I think it's clear that there's no reason to think that the D-branes and their states are sort of essentially a part of what the nature of black hole entropy is, even within the string theory context.
So I would say things like, I mean, I agree that one can of course construct black holes, many different types of black holes from different systems of D-branes. I think what this argument does illustrate is that using these dualities, the black hole entropy is related microscopically to the entropy of those D-branes, microscopic D-branes. Of course, supersymmetry is a key ingredient in the argument. So this whole thing works in this particular case because of supersymmetry. So that's why we can identify the configuration of the black hole with the D-branes. This is not meant as, you know, a general explanation. I don't think they meant this to be a general explanation for any black hole of where the microstates come from. It's just an explanation for this particular black hole, which might generalize to other cases. It might not. But for this particular black hole, we have a robust calculation, and we can tell that this, at least the evidence points to the fact that D-branes really account for the entropy of the black hole for that calculation. So I think that's the interest of, and I think that's also what they claimed in the paper. So there is a specific mechanism for these black holes that gives us better understanding of. I mean, there are not many black holes for which we have an actual microscopic configuration for which we can do that. So if you find one black hole, I think that's by itself already quite significant to find such a mechanism in string theory.
So you said that this shows that D-branes, quote, really account, unquote, for the black hole entropy. I think that's really a dangerous statement. I mean, it's true that the D-brane counting agrees with the black hole entropy, but that doesn't mean that the quantum states that the black hole entropy refers to are somehow these states of the D-brane that have been counted, because as you said, they've been counted in a very different regime of the coupling constant. So the argument, it seems to me, only establishes that accounting of one thing over here and accounting of another thing over there must yield the same result because of this supersymmetry non-renormalization property. But that's very different from saying that the states of the D-branes account for in the sense of, ontology that you mentioned.
No,
the black
so
hole
yeah.
entropy states.
So when I mentioned, so let's see, there are two types of identity. One is identity in the sense of ontological identity, that this would be the same system. But I've already said that we don't think that's the case. But there is this other weaker sense of emergence, in the sense that when we increase the coupling, the duality leads us from one set of states to another set of states. So I think what the statement of Strominger Vafa is that not only the number of D-branes, so not only the numbers is the same, but also there is a perturbative match between the Hilbert spaces, so that's what you need to. So there is this approximate duality requires some type of isomorphism, perturbative isomorphism between the states. So it's in that kind of perturbative relation so it's in this emergent sense that I think that that it accounts for the states. It's not accounting for in the sense of it is the same system, because we don't think it's the same system.
Thank you for a nice talk, Sebastian. There's one general question. I'm only expecting a general answer, but in principle, I would only consider one theory to be dual to another, or one theory to be equivalent to another, if I could find a mapping of all states in Hilbert space in one theory to all states in Hilbert space in another theory, such a way that the evolution operator is basically the same. But I guess you can't go that far yet in all these claims. So what is it that people do to do the administration of Hilbert space?
Yeah. So, so the administration is best done in the near horizon limit. So in that case, there's a more explicit kind of bookkeeping. So in the near horizon limit, you have you approximate ADS-CFT. So in that case, the Hilbert space of the D-brane systems of the Young-Mills theory and the D-brane of the closed string theory is. So in that case, there is a systematic duality map which gives you all the correlation functions. I mean, I guess you know this. It gives you the correlation functions of the CFT from the observables in the string theory, in the supergravity approximation. So there is a systematic approximation that in that near horizon limit gives you the states of the quantity and the quantities. And so there it's much more explicit. And in some of these calculations that people have done later on, like the Callan-Maldacena BTZ approximation, that can be done much more explicitly. It is still not at the level that we have. I mean, what we would really like is we would like a kind of formulation, an explicit formulation of the Hilbert space, where we can see that these two systems, these two descriptions, are representations of the same Hilbert space that reserves all the quantities. Even in ADS-CFT, there isn't something like that, but at least there is a systematic respect to that. So basically, the n correlation functions of the CFT correspond to the fields in the bulk with certain boundary conditions, and the boundary conditions are given by the kinds of background fields that you have in your CFT. And so that is also true in the near horizon.
Okay, we have time for just one more question. Fortunately, we've built in a very healthy buffer for a long lunch, and lunch is being served right outside the door, so Professor Mavo.
So I'm going to make a pretty rhetorical comment here. I don't know this stuff very well. I've looked a little bit at ADS-CFT, and physicists sometimes use a strange terminology, like they'll call it the ADS-CFT theorem, and you immediately find there's no such theorem. And not only is there no theorem, I can't get anybody who'll give me a clear statement of what the conjecture is. And at the end of this, you said, well, this is somehow very impressive. But what impressed me when you went through the history was that you say, well, they thought maybe there was a conjecture, there was some duality, and on the basis of this conjecture, they did some calculation in an extremal situation where the entire mass is by the charge, has nothing to do with astronomical black holes in the wrong number of dimensions, and then they took these limits. What impresses me in this history is how thin all this stuff is. And at the end of the day, I keep hearing physicists say, oh, we've done these calculations, and we think because of these calculations, this must be the... I mean, I just don't understand the kind of optimistic tone. And maybe I missed something. But to me, this looks like kind of a castle built on sand.
Okay, thank you for your comment. So impression factors are quite subjective, so I try to use an objective account. I think I've been quite clear about what has been achieved, what has been not. I leave it up to you to think whether you think it's impressive or not. I think one has, furthermore, our historical philosophical project, what it aims to do is to explain why from the standards of the community. So we haven't really looked at how this has been, at least in these papers, how it has been received. So our aim was to explain why it was received by the community in this optimistic way that you referred to. I think my talk has not been either optimistic or pessimistic. Actually, I think we have taken a pessimistic take by saying, well, there isn't a duality. There are all these generalizations that you need to do. So I think as philosophers, our job is to show what has been done. But there is an important historical question about why it was received in the way it was in the community. And I think there's a good evidence why that was. Namely, it uses principles of duality and so on that were kind of well entrenched in the community. So that's basically our statement.
This is the final remark by Professor Uva.
Just a one-line follow-up to Tim. Your talk was very good, but I think what it shows is what Tim says. The formula you started from, entropy, area with fundamental constants, is so simple, so beautiful, so clear, so looking fundamental, that the day we're going to say, we understood it, we will understand it in some simple manner, not through an horrendously complicated piling up of conjecture, D-branes, and all this complicated story. I think that will come out from the entire analysis, beautiful analysis of what has actually happened in the history.
Yeah, I mean, sometimes one has to find a very complicated or a lengthy calculation before one is able to reformulate it and understand it in a much better way. I think the development, in some sense, one can see the developments that came later as the enhancing of the attempts to better understand and better formulate. For example, the Carol-Maldacena calculation was already dispensed with one of the steps by doing the calculation directly for the open strings on the D-branes. So they did not need the Yang-Mills here, so that was already one simplification. So what they did is they calculated they counted the number of configurations that open strings can have on configurations of D-branes. So that was a calculation with a much more statistical mechanical flavor. It was really a combinatorial calculation. How many strings do I have? How many D-branes? How are they distributed? How can I test them? So that was already a simpler calculation. Of course, one wants, and you are working on this, many people are working on this, on getting a better understanding. I think no one is claiming, I think string theorists also don't claim that they have kind of an ultimate understanding of something like that.
Well, let's thank our speaker again.